There are times at which our particles, they will be unstable. And when particles are unstable, they will want to become something more stable. So when that happens, we have what we call a radioactive decay. And that happens in three different ways. So we have alpha decay, right? Alpha. We have beta decay, and we have gamma decay. So there's alpha, beta, and gamma decay. And each one has its own properties and characteristics. But before we talk about those in detail, specifically about each one of them, let's just come up with some names. So the first name that we should understand is nucleons. So what are nucleons? Well, usually we know what protons are, what neutrons are, what electrons are. Nucleons, as the name basically implies, it's how many particles do you have in the nucleus. So it's your neutrons and your protons. So in a way, it will give you how large the mass of your particle is, because neutrons and protons, they are actually the massive particles in an atom. The electrons, they are basically massless, or well, compared to the nucleons, compared to neutrons and protons, electrons, they have neglective mass. And we could say that this is the same thing as the mass number, right? So if you look at your periodic table, you will see mass numbers. That would be the number of nucleons. Now, just remember that in your periodic table, many of the quantities, they are not whole numbers, because in nature you have some variation of numbers of neutrons in atoms. We call those isotopes, right? So since you have different isotopes, when you look at the periodic table, you might find your mass number to be something which is not a whole number, but usually the numbers which are going to be given to you on the IB exams will be whole numbers. And when you're talking about particles, specific particles, you cannot have half a nucleon, right? So those broken numbers, they're good for an average understanding of the particles, for an average understanding of each of the atoms and its properties, but not for working with single atoms, all right? So let's take an example of a substance. So C usually denotes substance, carbon, right? And if you look at your periodic table, you should see that carbon has two numbers close to it, right? 12 and 6. So what do those mean? Well, 6 is the number of protons. And this is what defines that this substance is carbon. If it had a different number of protons, it would be something else. It wouldn't be carbon. Now, this 12 here is the number of nucleons. So it's the mass number, what we call the mass number. So it's protons plus neutrons. Therefore, I can already calculate that the number of neutrons for this isotope of carbon is 6, right? Number of neutrons. Because if this is 12 and I've got 6 protons, I've got 6 neutrons. Now, there is another isotope of carbon which we find in nature, and that's carbon-14. That's the one that we use for carbon dating, for trying to measure how old things are. So in this particular case, we still have 6 protons, otherwise it wouldn't be carbon. However, there are more neutrons now. So I've got, there are 8 neutrons. So it's a different number of neutrons. And this is not stable. So this carbon will want to drop, right? It will want to lose some of those neutrons. It wants to get rid of them and to become more stable. So by observing the ratio of carbon-14 and carbon-12 on old things that we find, like soil, fossils, anything we find, really. We use carbon dating to detect how old things are. And this is closely linked to a concept called half-life, which is the time that it takes for half of a substance to decay to its more stable isotope. But we'll discuss that later. For now, what's important for us to understand is how do we denote those substances, those elements, and what each of those mean. Now, a question that some students usually ask is, sir, if there is a nuclei full of protons and some neutrons as well, how come those protons don't split apart? If they are all positive, they want to repel each other, don't they? So there is some electrostatic repulsion. Yes, however, there is also the strong nuclear force. Which is one of the four fundamental forces in the universe. So this strong nuclear force is the one that's binding them together. It's stronger than the electrostatic repulsion force. And what we're going to observe is, the smaller our atom, usually more stable it is. Well, because you've got less things to keep together, right? Can you imagine if you're trying to hold like several pieces together, right? Here, all of them are really close, so the force of, for example, this particle, let me just change the color. So the force of attraction of this particle and this one is really strong because they are close together. So they are all really tightly bounded. However, take a look now. This particle here, which let's say is a proton, and this is also a proton, they are really far away now. So the repulsion force is still there, and the strong nuclear force, even though it's still there, it's weaker. The strong nuclear force is only strong at very, very small distances. So when we increase this distance, it becomes unstable. So we will observe that when atoms want to become stable, they will want to, for example, break apart, and they will release chunks of themselves to the environment and then become a more stable substance. And they might change, they might become another element. That happens. If it loses protons, then the new substance will be completely different to the previous ones. And despite what people usually think, because we live in a macroscopic world, whenever we change like the tiny bits of our universe, like what we're doing here, the atoms, the new substances, they might have completely different properties. The chemists are more used to it than the physicists usually, because, for example, you see table salt, which is sodium chloride, and that's you can eat that, right? It's something harmless to us. I mean, you cannot eat too much, you're gonna have problems, but it's something that's actually good for your system, right? You need salt. If you don't have salt, you also die. However, if you split them apart and you get only sodium and only chloride, if you eat or drink any of those, you die. If you breathe this in, you die. This burns, like combusts in the atmosphere. So that's really complicated, isn't it? So the properties of our substances, they will change, and they might even become completely new atoms. So I'll show you some examples now. So the first kind of radioactive decay that we're going to study is alpha decay. A note that I think is important to mention is that those names, alpha, beta, and gamma, they were given much before we knew about most of the structure of the atom that we know nowadays. So, for example, we know now that alpha decay is actually a helium particle. It's mass number 4, atomic number 2, so we know that, but back then we didn't, so we just called it alpha. Alright, so you know now that alpha decay, your atom will be releasing a helium atom. So it's been split. Somehow the forces here, this is random, it's, as we say, random spontaneous. It happens in nature, you cannot predict, but if you wait long enough, you will see that it follows some probabilities that we'll discuss later. But basically, at some point, another terminology that's important to remember is parents and daughters. So basically, again, something that's quite old, but the origin particle, so the particle that you had before the decay, is called parent, and the particle that you have after is called your daughter particles. So you have your daughter here, which is going to be something less massive, a bit less massive, and your alpha particle. So the examples that we have here, for example, uranium undergoing alpha decay, releasing a helium atom and becoming thorium. The maths here is quite simple. Take a look, 238 is 4 plus 234. This is the conservation of mass. Mass is not going anywhere. It's not vanishing, not disappearing. So we have a conservation of mass here. The mass number has to be the same. Also, the number of protons has to be consistent. So if I had 92 protons before, I still need to have 92 protons after. So I've got 2 here on this helium atom, which gives me 90 left for the thorium. Now thorium can also undergo alpha decay, and then it will become radium. You can observe here again, 90 is 88 plus 2, and 234 is 230 plus 4. That's okay, isn't it? Now, in the negative beta decay, the unstable nuclide will emit 1 electron. So, since it's shooting off an electron, the mass number will not change because the electron has virtually, basically, negligible mass compared to those ones. However, there will be charge. So we can see that the charge was 53, and now that I've got another negative one, I need 54 less 1 to get 53. Some of you might argue, oh, did I just create negative charge here? Well, not quite, because what's happening here is that one neutron is splitting, and it becomes a proton, an electron, and an antineutrino. And the antineutrino is the first subatomic particle that we're looking at. Well, the electrons, technically they are as well, but this is the new thing, right, that you have never, well, perhaps you've heard about, but you haven't studied before. So again, a neutron, which is inside of here, becomes a proton, and then it emits an electron and an antineutrino. This decay usually occurs on those nuclides with a too high neutron-proton ratio. You don't have to memorize that, but that's some relevant information. And we'll discuss more about those antineutrinos and the other subatomic particles in 7.3. So let's take a look at those examples. So we have iodine becoming xenon, and it's releasing an electron and an antineutrino. We can see that the charges, this is 0, 0. It's not written, but it's 0, 0. So it has no charge and no mass. So 131, 0, 131. And 53 equals 54 minus 1. Here we've got thorium becoming pallium, and then releasing an electron and an antineutrino. Again, what's happening here is that one neutron in the nuclei will become a proton, and it will release an electron and an antineutrino. Okay, we'll see more of that later on. That's quite interesting. Now there's another notation for this, because now we know that it's an electron, but as I was telling you before, back then we did not know, so it's common also to see this instead of this. Okay, so beta. There's also positive beta decay. So the difference now to the positive beta decay is that instead of shooting off an electron and a neutrino, an antineutrino, we will have a positron and a neutrino. Now, the positron is the same thing as the anti-electron. So the anti-electron, you always have one which is the antiparticle, and this is not antiparticle, this is neutrino. But in this case here, you have an antineutrino and an electron. So you have a particle and an antiparticle. Here it's an antiparticle and a particle. Students sometimes forget about the neutrino and the antineutrino because it's always 0, 0. So they don't miss any numbers, and they forget to put the neutrinos or the antineutrinos here, but you will lose your marks if you don't. This expression, those expressions that we have been dealing with, are called our equations, our decay equations. So if they ask you to draw or write the decay equation for carbon undergoing positive beta decay, then you should be able to do the second part here, or at least to find out, okay, what's the mass number, what's the atomic number of your products. Now again, the same maths will hold. For example, here in this one, sodium becoming neon and releasing a positron and a neutrino. So sodium, mass number 21, there is mass 0, so it's still 21. Now the mass was 11, and I've released a positive particle, so my positive atomic number here has decreased by 1. My positive particles have decreased by 1. And what is happening here inside of our nucleus is quite the opposite of what happened here. So instead of a neutron being converted to a proton, it's the opposite. A proton is being converted to a neutron, right? And a positron, obviously, a positron will be ejected. Now, the last kind of our radioactive decays is gamma ray emission. Now, gamma rays are actually high energy photons which are often accompanied by other decay mechanisms. So usually when particles they undergo alpha and beta decay, the daughter particles, they will be in a quite excited state. So it's really common for those results, right, those products to undergo gamma ray emission afterwards. So they basically become stable by releasing a photon. So in this first case here, it's showing you all the whole process, not only gamma ray emission, but combined with another decay. Are you able to find out which one is it? So since you're shooting off an electron, what's going to happen here is that, well, that's beta minus, right? Beta minus decay, and then gamma radiation. So you see here your nickel, and becomes nickel, but with some gamma radiation. This asterisk here denotes that this particular atom is in an excited state. So you want to give off some energy, and this is the energy that it's going to release. Now, if you observe, this nickel is the same as this one, so you could actually even combine both equations here. So we would have cobalt shooting off an electron, and I'll just put our anti-neutrino here first, plus. Now, so I've put this one and this one. Now take a look. This nickel, it will not stay like that for long. It will also decay, emitting gamma particles. So I will put those two products here. So we will have our nickel in not an excited state, plus, and then we would have this gamma and this gamma ray. So it's actually two gamma rays. So two gamma photons are going to be emitted in this radioactive decay. And again, this is called the decay equation. So let's take a look at those two quick examples so we can apply the concepts that we have learned so far. So number one, a nucleus of strontium-90. So we're given here, usually they will give you the information about the elements. You won't have to memorize or look into a periodic table. So strontium-90 decays into an isotope of yttrium by negative beta emission, right? Negative beta. Write down the nuclear equation for this decay. Now I'll repeat this again, but you can always pause the video and try it yourself before you move forward, okay? But, so write the decay equation, write down the nuclear equation or the decay equation. So how does it work? Well, first we have strontium 90, 38. And let's say that I don't know what's gonna be here. Well, I know that it's white true, okay? And I'll have here, since it's beta decay, right, negative beta, I'm shooting off an electron. Electron have virtually no mass and negative charge. Remember, negative beta, so that means the charge will be negative. Positive beta, this charge would be positive. And we cannot forget about our anti-neutrino. You don't have to put those zeros, but I always do. And here, yttrium 90 and 38. For you to be consistent, you would need 39 minus 1. Simple. Now number two, under certain circumstances, a nucleus can capture an electron from the innermost shells of electrons surrounding the nucleus. When the iron 55 nucleus captures an electron in this way, the nucleus changes into manganese nucleus. Write a nuclear equation to summarize this. So in this case, it's not necessarily a decay, but we should be able to draw, to write our nuclear equation. So I've got iron, and this iron is becoming manganese. And basically we're told that it absorbs an electron before, and then it becomes manganese. So I will add an electron here. Okay? So let's put the numbers in. So electron, mass 0, charge -1. So my iron will decay its charge by 1, and its mass will remain unchanged. So that's why it becomes manganese, because we have changed the atomic number. And that's it. Next topic, half-life.